Welcome back. In the last lesson, we had introduced the concept of similitude. We also introduced the non-dimensionalization of the governing equations and the boundary conditions as a method to explore similitude. We started doing a problem in which we considered the flow past a sphere. Any dependent variable like velocity Vx is a function of the independent variables x and the independent parameters like velocity V naught far away, P naught the pressure far away, the material property density, viscosity, the acceleration due to gravity, and the geometry of the body, which includes its size represented by the diameter here. Similarly, any dependent parameter like lift would depend only on the independent parameters and the shape of the boundary. We non-dimensionalized by introducing the non-dimensional variables. X star is equal to x by d, z star is equal to z by d. The velocities u star and w star by dividing them by the free stream velocity V naught, and the non-dimensional pressure P star as P divided by the pressure far upstream. The quantities used for non-dimensionalizing the various variables are those that are characteristic of the problem. The non-dimensional equations that we got after some manipulation are these. In these equations, the independent parameters are now collected together, and these are the only three locations the independent parameters occur. The boundary conditions become this. There are no independent parameters in the boundary condition except for the shape of the body. Now, this represents a great saving from initially a dependent variable being function of independent variable x star and the independent parameters, 6 of them. Now we had only 3 groups of independent parameters. These 3 independent groups of parameters, P naught divided by rho V naught square, Gd by V naught square, and mu divided by rho V naught d, are termed as pi numbers. Note that these are all dimensionless. Thus, non-dimensionalization has reduced the number of independent parameters from 6 plus the geometry to only 3 plus the geometry. This is a significant improvement in that if we were developing a database for solutions to this problem, we would not need to vary the 6 parameters over their entire ranges, but only manipulate these 3 pi numbers over their range of values. The result obtained with one set of values of dimensional parameters could be used to predict the result for many more sets of these parameters as long as the values of these pi numbers are equal. We introduce the concept of similarity in the following words. The two flows, the model and the prototype flows, are similar if the values of the non-dimensional pi numbers formed with the uniquity parameters are identical in two flows. In such situations, the normalized dependent variables have the same values on all set of homologous points. Homologous points are those points which have the same values on non-dimensional locational variables in the model and the prototype. This statement was broken down into two parts. A, the modeling rules, the requirement of similarity. Two flows are similar if the values of the pi number formed with independent parameters in the two flows are the same, and the prediction rules. If the two flows are similar, the values of the normalized dependent variables and parameters in one flow are the same as in the other flow at homologous points. Let's do one example to illustrate this method. We are required to estimate the power requirement of a blimp, which is a lighter than air aircraft, traveling at 10 meters per second in air. It is proposed to test a 1/20th scale model of it in water. What should be the velocity of the model in water, and what will be the prediction rule for the power required if we measure the power from the blimp, model blimp? Similarity in this flow, like in most flows about immersed bodies, require matching of just the Reynolds number, since there is no free surface of cavitation in the flow. This was explained in the previous lecture. The characteristic pressure difference in this case can be taken as 1/2 rho V naught square, where the symbols have their usual meanings. This is possible because there is only one pressure. So the pressure difference is not defined a priori. So we begin with 1/2 rho V naught square. The matching of Reynolds number gives the following as the modeling rule. The value of the Reynolds number in model and in the prototype should be identical. And if we manipulate this, the characteristic value of the velocity in the model should be the characteristic velocity in prototype multiplied by LOP divided by LOM. That is the characteristic length of the prototype divided by characteristic length of the model into density of prototype divided by density of model into viscosity of model divided by viscosity of prototype. This is just recasting the Reynolds number equality in a different form. Here, everything on the right hand side is known. VOP is the velocity at which the prototype moves, and so the velocity at which the model moves is evaluated at 15.7 meters per second when you plug in all the values. So we need to move the model blimp at a speed of 15.7 meters per second to have a flow similar in the prototype which is moving at 10 meters per second. The power is required to overcome the drag. And the drag at such speeds for bodies like blimp are dominated by pressure drag, which is the flow-wide component of pressure force integrated over the entire blimp surface, or that the drag D is integral over the entire surface of P minus P naught into I, that gives the force in the ith direction, dot dA. I dot dA is the component of area in the x direction multiplied with the pressure gives you the x direction pressure force. And this is equal to the integral of the entire surface of the gauge pressure multiplied by I dot dA. That is the area in the ith direction. normalization of the right hand side using the characteristic pressure difference as 1 half rho V naught square and AC as the characteristic area gives drag is equal to 1 half rho V naught square times AC into the integral of P star G I dot dA star. Now this integral is non-dimensional. So if the flows are similar, the model flow and the prototype are similar, then the value of this integral would be identical in the two cases. So drag divided by 1 half rho V naught square times the characteristic area should be the same in model as well as in the prototype. The right hand side is same, so the left hand side must be same. So drag would be proportional to rho V naught square times the area. And the power required, the ratio of the power required would be the ratio of the drag times the ratios of the velocity, since the power is drag times the velocity. So the ratio of the powers Wp by Wm would be rho V naught cube AC for the prototype divided by rho V naught cube AC of the model. Whatever area we may take as the characteristic area, the ratio ACP divided by ACM will be equal to LP square by LM square. The characteristic length of the prototype square divided by characteristic length of the model square, which is given as 20 square. The length scale factor is 20. So this area ratio is 400. And the prediction rule of the power required becomes Wp is equal to rho V naught cube AC P divided by rho V naught cube AC M into Wm, and we plug in the value to get 0.125 Wm. Thus, the prototype would require only 1/8 of the power that the model uses. The model is smaller, then why is it using more power? Because it is being towed in water rather than air. Water is more dense, so the pressure forces are larger in water. Now we introduce another technique. This technique is known as the scale factor approach, and this is far more general and powerful, and it does not require a mathematical model to begin. Consider a model and a prototype which are geometrically similar. If the bodies are geometrically similar, this means that the ratios of all corresponding dimensions in the prototype and the model are equal. Thus, the ratio of the radius of the nose in the prototype to the radius of the nose in the model is the same as the ratio of the chord of the prototype to the chord of the model. And let that ratio be represented by K sub L. This is read as scale factor for length, K sub L. This is the ratio of the length of the prototype divided by the length of the model. So, in other words, the geometric similarity requires that there should be a unique scale factor KL for all lengths. whatever be the lengths. All lengths in the model can then be obtained from the corresponding lengths in the prototype through the use of KL. Next, we introduce the concept of homologous points. Consider a point AP in the prototype, a point AM in the model is termed as a homologous point if the ratio of the x coordinate and the y coordinates of these 2 points are exactly equal to KL. XP by XM is equal to YP by YM is equal to KL. In other words, if we enlarge every dimension of the model and the flow picture of the model by factor KL, then it will superpose the prototype exactly, and the point AM would then lie exactly over the point AM on the prototype. Every length, every coordinate is scaled by the same factor KL. Complete similarity implies that the same holds for each of the other quantifiable quantities, parameters and variables, both dependent and independent, such as velocity, time, stress, power, etc. This is to say that the value of any quantity at a point in the prototype is related to the value at the homologous point in the model through the corresponding scale factor. There is a unique scale factor for velocity, a unique scale factor for time and time intervals, a unique scale factor for all stresses, shear stresses, normal stresses, a unique scale factor for all forces, a unique scale factor for power. For example, the velocity at a point in the prototype is related to the velocity at the homologous point in the model through the velocity scale factor Kv. If, for instance, VOP, V1P, V2P and VOM, V1M, V2M are the velocities at homologous points in the prototype and the model respectively, then similarity of the two requires that V1P over V1M is V2P over V2M, so on, all equal to Kv, the velocity scale factor. Further, it is not just the magnitude of the velocities that are so related, but the direction of the velocities at the homologous point must be the same. This would require that the individual component of velocities are also scaled by the same scale factor Kv. In this picture, not only is the velocity V3 in the prototype same as the velocity V3 in the model at the homologous point, but also the directions of the velocity is exactly the same. This means the components of velocities in the two pictures are related by the same scale factor Kv. This is true for all homologous points. So all velocities at homologous points in similar flows must have the same direction, so that the magnitude of the velocities and all their components are scaled by the same scale factor Kv. Now, what do we require for similarity? Ensuring similarity consists of obtaining scaling relationship for the values of independent parameters. Given a prototype experiment, we can construct a model experiment which will have a similar flow, but only if we select the values of the independent parameters, which were named uniquity parameters, properly, such that they ensure that all quantifiable quantities have the same scale factors at all homologous points. The basic strategy in obtaining these similarity rules consists of exploiting the fact the scale factors for the various quantities are not all independent. The interrelationships between the various scale factors are converted into relations between the independent quantities for the prototype and the model. Once the similarity between the prototype and the model is achieved by the proper choice of the independent parameters, it can be shown that the dependent quantities also have constant scale factors, and those scale factors can be predicted from the scale factors that have been used for the independent parameters. To begin this consideration, let's consider a small area in a prototype with one dimension dxp and another dimension dxp, dyp. So dap would be dxp times dyp. The homologous area in the model has the length dxm in the x direction and dym in the y direction. This is the homologous area in the model. Clearly, DAP, which is DXP into DYP, can be written as KL type DXM, since KL is the scale factor for all lengths, into KL DYM, the same KL, which gives you KL square into DXM into DYM, which is DAM, the model area. Thus, Ka, which is DAP over DAM, is nothing but KL square. Similarly, the volume scale factor Kv equals KL cube. Area has two dimensions of length, so the area scale factor has two KLs, KL square. Volume is three-dimensional length, so Kv is KL cubed. And the velocity scale factor is velocity in the prototype divided by velocity in the model. And the velocity in the model would be dxm divided by dtm. And this simplifies to dxp over dxm into dtm by dtp. The first one is KL, and the second ratio is the inverse of KT, because KT is dTp over dTm. So the velocity scale factor is length scale factor KL divided by the time scale factor KT. Again, the dimension of velocities are length into t minus 1. So scale factor of velocity is KL divided by KT. Geometrically similar prototype and models are said to have kinematic similarity if all the kinematic quantities such as frequency F, RPM N, angular velocity omega, acceleration A, angular acceleration alpha, volumetric flow rate Q dot, etc. have constant scale factors. One scale factor for frequency, one scale factor of RPM, one scale factor of angular velocity, one scale factor for volumetric flow rate, etc. So that we can relate the scale factors of kinematic quantities with the scale factor KL and KT or KL and KV. Usually in fluid mechanics, we use length and velocity as the primary independent parameters. So it is convenient to express the scale factors for various quantities in terms of KL and KV. And these are the values obtained using the method described in the earlier slides. Let's start with the scale factor of volume flow rate as an example, KQ dot. We know that KQ dot is like KL square times KV. Why? The volume flow rate through a pipe, for example, is equal to the velocity through the pipe multiplied by the cross-sectional area of the pipe. So the scale factor for volume flow rate would be the scale factor for area of the pipe times the scale factor for velocity, KL square times KV. This implies that QP dot divided by Q dot M, which is the value of KQ dot, the scale factor for volume flow rate, is equal to LP over LM, which is KL whole square times KV, which is VP by VM. We separate on the left and the right hand side the parameters and values corresponding to prototype, and on the other side the values associated with the model. And we get Q dot divided by L square V over prototype is equal to Q dot divided by L square V for the model. Here, these quantities are assumed to be characteristic quantity. L for the prototype and L for the model measure the same corresponding lengths. If in a aircraft wing we are talking of chord in one case, it has to be chord in the other case. If we are talking of the thickness in one case, then it has to be thickness on the other case. Whatever we choose as the characteristic value of the length. Similarly, V here is understood to mean that it is a characteristic velocity, which should be chosen same type of velocity in the two flows. So if in one flow it is the velocity far upstream, in the other flow also it should be the velocity far upstream. What does it mean? That the parameter Q dot divided by L square V is a pi number whose value must be same in the model and the prototype. It is understood that the quantities are the characteristic values. This is a requirement for similarity. If Q dot, L and V are independent parameters, but if one of them is a dependent parameter, it becomes a prediction rule. We'll explain that a little later. So we convert the relations between the various scale factors that we obtained earlier into pi numbers. These are the pi numbers using L and V, the length and velocity. For angular speed, frequency, RPM, the pi number is FL by V. FL by V in the prototype and in the model must have the same value. Alpha L square by V square is the pi number corresponding to angular acceleration. These must have the same values in the model and the prototype. Every one of these.